Section 2.1, Basics of Functions and Their Graphs. The first objective is going to be to find the domain and range of a relation. But first, we have to establish what we mean when we say a relation. A relation is any set of ordered pairs, and remember that ordered pairs are typically expressed using the two variables x and y. And ordered because the order in which they are listed makes a big difference, right? So I have some examples of some relations below, and the notation that I'm using is just saying this is example 1, 2, and 3. And these three examples are all certainly sets of ordered pairs, and so they would meet the definition of being a relation. The set of all first components, or the x values in the ordered pairs, is called the domain of the relation. And this set of all second components, or all of the y values, is known as the range of the relation. So every relation has a domain, the set of all the first values, or the x values, the x coordinates, and a range, the set of all second values, the y values, the y coordinates. So for the first example, the domain would include the x values 1, 2, 3, and 4. And we're using set notation here, so we're just putting a comma between each of the values. And the range is going to be 3, 4, 5, and 6. For the second one, the domain is going to be 2, -2, 3, and -3. And the range is going to be 4. So one thing that we have to talk about is because I have 4, 4, 9, 9. So when we're using set notation, we don't put repeated elements more than once. So the range on this one is just 4 and 9. And the same thing's going to hold true for example 3 on the domain. I only have 4 and 9. But the range is going to be -2, 2, 3, -3. So there's 3 examples of relations and the domain and range of each of those relations. Now, remember that the topic of section 2.1 is relations and functions, right? So what we now are going to think about is, what is the definition of a function? Well, a function is a special kind of a relation. And of the examples above, the relations e sub 1, the first example, and the second example are functions, but the third one is not. So let's scooch back up here and look at this. So example number 1 and example number 2 are both functions, but example number 3 is not. What's the difference? So pause the video for a minute, and that's the nice thing about having a video lecture, right? Is you can pause the video and think about it. So go ahead, I would invite you to pause the video and think for a minute. What's the difference between the first 2 examples and the third example? And so maybe you noticed, maybe you didn't, no big deal either way. A function is a relation in which each element from the domain is paired with one and only one element from the range. So if we look at example 1, 1 is paired with 3 and only ever 3. 2 is paired with 4 and only ever 4. 3 is paired with 5 and only ever 5. 4 is paired with 6 and only ever 6. If we look at example 3, which is not a function, it's a relation, perfectly good relation, it's just not a function. 4 is paired with both -2 and 4 is paired with +2. 9 is paired with 3 and 9 is also paired with -3. So this x value 4 and this x value 9 are both paired with 2 different y values. And it doesn't have to be only 2, it could be 2 or more, right? Example 2 is a function because 2 is only ever paired with 4 and -2 is only ever paired with 4. And it's okay for two different x values to be paired with the same y, just so long as this x is only ever paired with 4, and this x is only ever paired with 4, right? And it's actually easier to see if we use something called a mapping. So I have the 3 examples down here, and I have these circles that are going to represent the set of the domain and the set of the range for each. And we're going to see where each of the x values maps from the domain to the range for each of these relations. So for example 1, the domain, remember, was 1, 2, 3, and 4, and the range was 3, 4, 5, and 6. So this is where the mapping comes in. These are also sometimes called arrow diagrams. So 1 maps to 3 and only 3. 2 maps to 4 and only 4. 3 maps to 5 and only 5. 4 maps to 6 and only 6. And I can see that each of these x values is paired with one and only one y value. Now let's look at example 2. My domain includes 2, -2, 3, -3, and my range is the 2 elements 4 and 9, right? So 2 maps to 4 and only 4. -2 also maps to 4, but it only maps to one y value, right? 3 maps to 9, and -3 maps to 9. So each of these x values in my domain has only one arrow coming off of it going to the range, right? So 2 only is paired with 4, and -2 is only paired with 4. Now, the contrast is going to be clear when we do the mapping for example 3. My domain includes only 4 and 9, and my range includes -2, 2, 3, and -3. So 4 maps to -2 and +2. 9 maps to +3 and -3. And we can see the huge difference that this relation has as compared to these two. This x value has 2 arrows coming off of it, right? Going to 2 distinct different y values. Okay, so a question that might be coming to your mind could be, why do we care about this? Why do we define functions in this way? So let me give you an example that may seem kind of strange at first, but I want you to think about an oven in your kitchen. And I want you to think about making a chocolate cake, all right? And I want you to think about mixing up the ingredients to make a chocolate cake and putting those ingredients that are all mixed up and in the cake pan into the oven, right? So if I use this recipe, I get this is a recipe for chocolate cake, and out comes chocolate cake, right? This might be a recipe for cherry pie, and out comes cherry pie. This might be a recipe for lasagna, and out comes lasagna. This might be a recipe for, I don't know, pizza, and out comes pizza, right? Well, in this example, there's more than one recipe for chocolate cake, right? This could be my Duncan Hines chocolate cake mix. I put it in the oven. What do I get? Chocolate cake. This could be my grandma's recipe for chocolate cake. Put it in the oven. What comes out? Chocolate cake, right? So nothing strange going on here. But over here, let's say this is my recipe for chocolate cake, and I put it in the oven, and sometimes I get chocolate cake, and sometimes I get cherry pie. Now that is not a dependable tool, right? So I need to be able to count on my oven or my function, right, given a certain set of ingredients, right, or certain x value, to give me my expected value for y, right? Here, I'm putting in a 4, and I don't know what's going to come out the other end of my function or my oven, right? I might get a -2, might get a +2. Another example that we can think about is on my keyboard, right, of my computer. I have over here a keypad, and it has 1, 2, 3, 4, 5, 6, right? The numbers here. The numbers are also across the top of the keypad, right? If I press a 4 up here, what shows up on my computer screen? A 4. I could press this 4 over here, and I also get a 4 on my computer screen, right? Now, that's perfectly well-functioning keyboard, right? But if I pressed a 4, and sometimes I got a 4 on the screen, and sometimes I got a -2 on the screen, my keyboard would be broken, right? I wouldn't be getting an expected result for that input that I'm giving it, right? And the reason that we care about this is because functions are one of the most important constructs that we use in math, and we use them to model real life functions, right? Like cost or revenue or profit, right? And I want, given a certain input, my profit to be a function of that input, right? Given a certain input, I want my revenue to be a function of that input. So this is why we define functions the way that we do, and this is why we care about whether or not each input gives me one and only one expected output. Now, there are several ways that the more general idea of a relation can be represented. We've already seen 2 of them, as a set of ordered pairs and as a mapping. Another way to represent a relation is to use a graph. So let's create graphs for examples 1 and 3. Now, remember that we called these ordered pairs, right? X comma Y. And I've got below here a Cartesian plane, right? With my x-axis and my y-axis. And each of these ordered pairs represents a point on this plane, right? So if I want to plot the point 1, 3, then remembering that this is my x and this is my y, I'm going to start at the origin, 0, 0, right? And I'm going to go over 1 in the positive x direction and up 3 in the positive y direction. So there's that first point. The second point is 2, 4. So I'm going to start at the origin, 0, 0. I'm going to go over 2 in the positive x direction and up 4 in the positive y direction. And then for 3, 5, I'm going to start at the origin, go over 3 in the positive x direction and up 5 in the positive y direction. And then finally for 4, 6, I'm going to start at the origin and go over 4 in the positive x direction and up 6 in the positive y direction. So those are my 4 points in that relation plotted on my plane. Now I'm going to come over and do the same thing for example 3, and we're going to see what we notice. So for -2, I'm going to start at the origin, 0, 0, go over 4 in the positive x direction, and -2, so down 2 in the negative y direction. And then I'm going to start at the origin and plot 4, +2. So I'm going to go over 4 in the positive x direction and up 2 in the positive y direction. And then 9, 3, I'm going to go over, starting at the origin, I'm going to go over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9 in the positive x direction, and up 3 in the positive y direction. And then finally -3, starting at 0, 0, and going over +9, and then going down 3, -3 in the negative y direction, right? I can see the 4 points that are in that very simple relation as well. So my question to you is, can you tell just by looking at the 2 graphs, if I didn't already know that this one was a function and this one was not, would I be able to look at this graph and determine which one represents y as a function of x? I think I could, right? And if I looked at this point and I drew a vertical line through it, I'm not going to hit any other points on that graph, right? This means that this x value, 1, is paired with 3 and only 3. If I look at this point and I draw a vertical line, it's only ever intersecting, the vertical line is only ever intersecting the graph here at this 1 point, right? Because 2 is only ever paired with 4. The same thing for the green point and the yellow point. Now over here, if I draw a vertical line through the graph, do you see that it is hitting both the red point for +2 and the blue point for -2? So now when I see this result, I can see that this x value of 4 is paired with two different y values. And the same thing is true over here, right? I can see that not only is 9 paired with positive 3, it's also paired with negative 3. So I can tell by looking at this graph that this relation does not represent a function, and I can tell by looking at this graph that this relation does represent a function. And this result is known as the vertical line test. If any vertical line intersects a graph in more than one point, then that graph does not define y as a function of x. So the examples that we've seen up till this point have been very simple relations with only 4 ordered pairs. And of course, relations encompass a much wider set than just sets of specific discrete ordered pairs, right? And we can use this result to identify graphs in which y is a function of x that are more interesting than just 4 ordered pairs, right? So these are 4 examples that are taken from our textbook. And the first one is example number 57. And I can see that this horizontal line would most assuredly pass a vertical line test, right? So this one represents y as a function of x. It passes the vertical line test. And we can abbreviate that just VLT to same space, right? Now, the second example here does not represent y as a function of x because it fails the vertical line test, right? This one is not a function because it fails the vertical line test. Now, the next example does represent y as a function of x because it passes the vertical line test, right? And finally, this last example does not represent y as a function of x because it fails the vertical line test. And, as you're working through this with me, I hope that you had a chance to print out the guided notes, right? And that you're following along with me and you're stopping the video as needed to think and process and backing up and listening again if needed. It's really important that you are taking notes. If you, can't print out the guided notes, then definitely get yourself a notebook and be taking notes as we're working through this together, right? Just sitting and watching me and listening is not going to be nearly so effective as getting engaged in this lecture by taking notes and being an active participant, stopping, asking yourself questions, jotting down questions as you're working through it, right? You might, have a question for me as we've gone through these first 2 pages. If that's the case, make a note, highlight it, right? Put a little flag on it, and, either post a question in the discussion board or send me an email. But just sitting and watching isn't going to be enough to help you to process this and to create real neural pathways, real learning. So our third objective is to evaluate a function. And another way to represent a function is to use something called function notation. Now, when we're using function notation, we are not going to be thinking about relations. We're going to be thinking about that more specific subset of functions. And the special notation, f parentheses x close parentheses, which is read as f of x, represents the value of the function at the number x. And the f is just the name that I'm giving to this particular function. You don't have to use f. You'll see our textbook uses f of x, g of x, h of x. If you take a business calculus course later in your math career, you might see c of the x for cost. You might see r of x for revenue. But just note that in this context, what this means is f of x. So let's do a little practice evaluating the given functions at the values of the independent variables and simplifying. Now that's another thing that we need to talk about. The x is referred to as the independent variable, and f of x is another name for y, and y is the dependent variable. And if we think about the way we defined a function, the value of y depends on the value of x, right? Each x gives us a one and only one unique value of y. This is the independent variable. Once I've been given this, the value of y is dependent upon it. Independent, dependent. So for this particular function, we are given an expression that we need to evaluate, 2x minus 3, right? Our equation is y, or f of x, equals 2x minus 3. And one way that we can think about this, and it's often very helpful when we start evaluating functions, especially if we are going to evaluate it at another expression, right, like in examples B, C, and D, is to think of our function as being a template or a pattern or a rule to follow. So in this case, f of our input, and I'm going to put the word input, is equal to, well, what do I do with that input? 2 times the input minus 3. And this is a function because once I have been given my value that's going to serve as the input, or my expression, depending on the specific example, right? Multiplying that times 2 and subtracting 3 is going to result in a single distinct output, right? So oftentimes we think of a function as being like a machine, right? So here's my machine, not always an oven, right? Sometimes you'll see pictures of functions like this. In goes the input. This is the function. Does its work, chunk, 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 and out comes an output, right? And we want this output to depend on this input, right? Now we typically use the variables x to stand for the input and y to stand for the output, right? But we don't have to, right? I could put anything I want here. I could put the word input, I could put a star, I could put a heart, right? Whatever is here, I'm going to multiply 2 times that and subtract 3. The reason I'm making such a big deal about this is if you are a really visual person, then when we get to these examples, this kind of thinking is very, very helpful. All right, so let's look at the first example, f of -1. So the rule says 2 times the input, which in this case is -1, minus 3. And then, so 2 times -1 is -2 minus 3, which is -5. So f of -1 is equal to -5. All right, so that's all well and good, right? But now, when we get to example B, and we're asked to evaluate our function at an expression involving x, sometimes the fact that there's an x here and a different expression involving x here can be kind of confusing. Well, just think about it this way. I'm going to do f of the input equals 2 times that input minus 3, whatever it is, right? So this input is just a placeholder. Here, this is just a placeholder. I can put whatever I want here, and I just follow the rule. So in this case, I'm asked to find f of the opposite of x. So that's going to be 2. The rule says multiply 2 times whatever the input is, in this case the opposite of x, minus 3. So 2 times the opposite of x is -2x minus 3. So f of the opposite of x is equal to -2x minus 3. Okay, so we're going to do the same thing for example C. This time our input is the expression x plus 3. F of the input equals 2 times the input minus 3. So 2 times x plus 3 minus 3. Now it's very important that I put these parentheses around that expression x plus 3 because I need to multiply 2 times the entire expression. And if I don't put parentheses, that won't happen, right? And what those parentheses indicate to me is I need to distribute, right? So I'm going to end up with 2x plus 6 minus 3. So our next objective is to determine whether an equation defines y as a function of x. So we've seen how to determine if a set of ordered pairs determines y as a function of x. We've also, or defines y as a function of x. We've also seen how to look at the graph of a relation and determine whether or not that graph represents a relation that is a function, right? But another way to represent a function, as we've seen, is in an equation in y and x, right? Not every set of ordered pairs defines a function, and not all equations with the variables x and y define functions. If an equation is solved for y, and more than one value of y can be obtained for a given value of x, then the equation does not define y as a function of x. So let's look at some examples of this and see what we're talking about. So for example A, we're asked to determine whether each equation defines y as a function of x. And the first one says x squared plus y equals 4. So we need to take that equation, x squared plus y equals 4, and solve it for y. So when we say that again, what do we mean? We mean to isolate y on one side of the equation. And it's a fairly simple matter to do that, right? I just need to subtract x squared from both sides. And if I subtract x squared from both sides, it's going to add to 0 on this side, right? So I'll go ahead and write it out. We're going to subtract x squared from this side, and we're going to subtract x squared from this side. These are going to add to 0. And I'm going to end up with y equals 4 minus x squared. Right? Now, for any given value of x, the rule says square it, subtract that value from 4, and that is your value for y, right? And there is only one possible y value for each and every value of x. Think of a value of x and plug it in and see if you can get something different than one specific number. It's not possible, right? If I let x be 0, 0 squared is 0, 4 minus 0 is 4. If I plug in 1, 1 squared is 1, 4 minus 1 is 3, and only 3, right? So this one is yes, right? Now let's look at the next example. X squared plus y squared equals 4. If I try and solve this one, x squared plus y squared equals 4 for y. Well, what am I going to do? I'm going to subtract x squared from both sides again, right? And I'm going to end up with y squared equals 4 minus x squared. And I don't want y squared, I want y, right? So I need to take the square root of both sides in order to solve for y, right? And we've seen this, and if you're not remembering how to do this, remember, go back and watch the review videos on solving quadratic equations. In this case, I can isolate y squared, and I can then go ahead and use my square root property to take the square root of both sides to solve. And when I do, I'm going to end up with y equals the positive or negative square root of 4 minus x squared, right? And I can see that for a given value of x that's in the domain of this function, I'm going to get two different values for y, right? So if I let x be 0 again, 0 squared is 0. 4 minus 0 is 4. The square root of 4 is 2. So y is equal to positive or negative 2. So that one value of x gives me two values of y, and this one does not represent y as a function of x. It's a perfectly good relation, it's just not a function. In fact, if I was to graph this particular relation, it would look like a circle with its center at the origin and a radius of 2, and a circle would not pass the vertical line test, would it? It would not. I don't need to know that that equation represents a circle in order to be able to determine that it does not represent a function, though, right? Okay, so now example C, I have y equals the positive or principal square root of x plus 4. So for any given value of x, there's only one value of y. Again, let's use 0. 0 plus 4 is 4. Square root of 4, the positive square root of 4 is 2. So yes, this one does represent a function. It's already solved for y, right? It was in the process of solving this equation, where we had y squared equals 4 minus x squared, that we had to take the square root, and we had to recognize that there are two, right, solutions to that particular equation, both a positive root and a negative root. Here, y is equal to only the positive square root of x plus 4. So yes, it is a function. The fourth example, x cubed plus y equals 8. If I'm going to solve this one for y, if I subtract x cubed from both sides, right, I'll end up with y equals 8 minus x cubed. For any given value of x, there's only one value for y, right? So yes, this one is a function. And then finally, for example E, x plus y cubed equals 4. Well, if I subtract x from both sides, I'm going to end up with y cubed equals 4 minus x. And now I need to take the cube root of both sides, right? And if I take the cube root, it would be, in fact, wrong for me to include both a positive and negative root. So the cube root, taking the cube root of both sides, is going to lead to me having y equals the cube root of 4 minus x. And, just think about for a minute why I don't need to include, in fact, it would be wrong for me to include a positive or negative sign. If y cubed equals 8, then one real valued solution to this would be 2. In fact, that's the only real valued solution to this, because 2 cubed equals 8, right? Negative 2 cubed does not equal 8, because negative 2 cubed is equal to negative 2 times negative 2 times negative 2, which is in fact negative 8, right? So whenever you're taking an odd root to solve a polynomial equation, there's only going to be one root, right? You're not going to include both the positive and the negative. Again, up here with the square root, right? If I say that y squared is equal to 4, there are in fact two values of y that will give me 4 when I square them, right? 2 times 2 is 4, and negative 2 times negative 2 is 4. So anytime I raise a base, right, in this case my base is y, to an even power, right, then both a positive and a negative base there, right, will result in a positive number. That is not true for odd powers. An odd power of my base will always result in a number that's the same sign as its base, right? 2 cubed is 8. Negative 2 cubed is negative 8. So just be aware of that, right? It's called the square root property. We could be more general and call it the even root property. Okay, so now we're going to turn our attention to the second part of this section. We talked about the basics of functions, and now we're going to talk about the basics of functions, the graphs of functions. And so you can actually obtain quite a lot of information about a function from its graph. In fact, it's often easier to obtain information about a function if we have its graph to look at, right? Visuals are so helpful, right? A picture's worth 1,000 words, right? So the first thing that we're going to think about is the domain and range of a function, which are much easier to determine by looking at the graph of a function than the equation or the function definition very often. So the first one example that I have here on the left is this function that would certainly pass a vertical line test, right? And when we're thinking about the domain, right? Remember that the domain is a set of inputs, right? The x values. So it's going to be found on the x-axis. And the range, of course, is the set of outputs or y values, and it's going to be found on the y-axis. Okay? And when we were doing domain and range before, we were given a set of 4 ordered pairs. And our domain and range for those examples included just a set of distinct numbers, right? Specific x values, 1, 2, 3, 4, 3, 4, 5, 6, right? Now, in this case, this is quite different because the domain is not a set of distinct or discrete values, right? It's this whole range from this point on to this point, right? And there's an infinite number of x values between any two given x values on an x-axis, right? So same thing for the range here. It's not a set of distinct x or y values. It's this whole interval along the y-axis, an infinite set of numbers. So we're going to use something called interval notation to report the domain and the range for given values. And I can see that because there's a closed circle where the graph begins and there's a closed circle where this graph ends, then both endpoints are going to be included in the domain. And when I include the endpoints in an interval, I use square brackets, right? So square brackets indicate endpoints that are included in an interval. And to contrast over here, this is a closed circle. I've got a bracket to indicate that point is included. This endpoint, though, has an open circle. So this endpoint is not included, and I'm going to indicate that using interval notation as a parenthesis. So parentheses indicate endpoints that are not included in an interval. And when an endpoint more generally includes either positive infinity in this direction or negative infinity in this direction, then parentheses are always used. Okay, so let's look at a specific example of this idea. So for these examples, we have some actual numerical values that we can look at, right? And we are told that this endpoint is included because I see a closed circle. This endpoint is not included because I see an open circle. And I'm going to go ahead and I'm just going to trace down to my x-axis. And I see that the first x value that is part of my domain is -2, and I'm going to put a bracket because that -2 is going to be included. And then I'm going to trace down to my x-axis here. And I see that since that endpoint is not included, I'm going to put a parenthesis there on 1. And so the domain of this particular function is going to be using interval notation from -2, including -2, to 1, not including that endpoint of 1, right? So the bracket here is a reflection of this closed circle, and the parenthesis here is a reflection of this open circle. Okay? So let's go ahead over here to this next one and talk about the domain on this one, and then we'll come back and think about the range of both of these. Now, when I'm looking at this one, of course, my x-axis extends in this direction towards positive infinity, and in this direction towards negative infinity, right? And this particular function, this arrow indicates this keeps going forever, right? So my domain doesn't have a specific beginning point, right? It's going to be from negative infinity up to and including this endpoint of 4, right? So 4 is the endpoint that's included. Negative infinity is always with the parenthesis. So for this one, the domain is from negative infinity to 4, including 4 because of that closed circle, right? So that's domain, right? And most people don't have any issues or struggles with domain. It's range that tends to be more of a problem. So let's think about that. So when I'm thinking about the range, what I often like to do, and I know you can't do this with your paper, but you can turn your paper. So what I'm doing is I'm going to go ahead and I'm going to take this piece of my function, right, a picture of my function, right, and I'm going to bring it down here, and I'm going to turn it so that my y-axis is horizontal, like I'm used to reading a number line, right? This is my y-axis. And remember that my range is along the y-axis, and I'm thinking about it in terms of what y values serve as outputs, right? And I can see that it's going to begin at positive 1, right, including that value. There's no open circle here. 1 is included. So I'm going to have a bracket on 1, and that's going to extend up to and including 5, because the 5 has a closed circle. It's a part of my outputs, right? So turn your paper on its side so that your y-axis is horizontal, like we're used to seeing a number line. And that's the biggest problem I think that people have with the range, is that this number line is vertical, and we're not used to seeing and reading a number line that's vertical. So turn it so that it's horizontal like you're used to seeing it. So the range for this particular function is from 1, bracket including 1, to 5, bracket including 5. Now, the same thing we're going to do with this second example over here. I'm going to go ahead and I'm going to copy it so that I can turn it on its side, and I can see that y-axis horizontally like I'm used to seeing one, right? And I can see that the first y value that appears as part of my set of outputs is going to be 0, right? That closed circle tells me I am going to get 0. So I'm going to put a bracket there. And then this arrow that extends this way, towards what? Towards positive infinity, right? Tells me that there is no ceiling or limit, right, on the y values. So I'm going to put parenthesis there, right? So my range for this particular function is going to begin at 0, including the 0, and extend towards positive infinity. And that's much easier to see if I think about that y-axis as being a number line more horizontally, right? So turn your paper so you can see it. Or turn your head, right, as you're doing your homework in my math lab. Just turn your head sideways and think of that y-axis as being a horizontal number line, right? So from 0, including 0, towards positive infinity. We can also use the graph of a function to determine the function's value for any given input, and vice versa. For an output, we can determine what inputs gave that to us, right? So let's use the graph of our function f. And the picture of it is here to the right, and this would be a function, right? It would pass a vertical line test. And we can use this graph to find each indicated function value. So for the first part A, we're asked to find f of negative 2. So I'm going to go on my x-axis, starting at 0, right, and find negative 2. And then I'm going to see what y value is associated with an x value of negative 2, right? So this ordered pair right here is negative 2 comma negative 4, right? So if x is negative 2, what is y? Negative 4. So we're using basically this picture is like a map, right? And these are my directions. Go to negative 2. Where will you end up? At negative 4. Now f of 4, here's my x value of 4, right? The ordered pair with x of 4 is 4, 4, right? So f of 4 is equal to 4. F of negative 3, so starting at 0 and going to x value of negative 3, that's negative 3, what's the y value there? 0. So f of negative 3 is equal to 0. Basically, what you're doing with these kind of problems is they're giving you the x-coordinate, right? You find that point that has that x-coordinate, and there'll be only one, right? Because we're talking about a function. And then you tell what the y value is, right? That's the y. Now, for part D, we're going to use the graph of f to find all values of x for which f of x, in other words, y, right? Remember, f of x is another word for y equals 0. So there can be more than one value of x that gives you 0, right? And it's still a function. And where is y equal to 0? Y is equal to 0 on the x-axis, right? So there's a horizontal line already there. It's the x-axis. It's y equals 0. So where does the x value, or what x values give me a y of 0? Well, here's one. Negative 5, 0. Negative 3, 0. Negative 1, 0. 1, 0. 3, 0. And 5, 0. So there are, in fact, 1, 2, 3, 4, 5, 6 values, right, of x that give me a y value of 0. So all the values of x include negative 5, negative 3, negative 1, 1, 3, and 5. Now, part E says use the graph of f to find all values of x for which f of x equals 4. So in other words, y equals 4, right? And this time I don't have a horizontal line already drawn for me, so I'm going to go ahead and draw one in at y equals 4. Now, there are 3 points, right? Here, here, and here. What x values gave me 4? Negative 4, 0, and positive 4. So if x equals negative 4, I get a y value of 4. If x equals 0, I get a y value of 4. If x equals positive 4, I get a y value of 4. When we look at the graph of a function, there are points on the graph that are of particular importance to us. And the first one is an x-intercept. An x-intercept is the x-coordinate of a point where the graph intersects the x-axis. So for this one, this would be an x-intercept here, and this would be an x-intercept here, right? So the x-intercepts for this particular graph would be 1 and negative 3, right? So the graph of a function can have many x-intercepts, right? And it would still pass a horizontal line test. The zeros of a function are the x values for which the function is equal to 0, for which y equals 0. We call those the zeros of a function. Therefore, the real zeros of a function are found at the x-intercepts. This gives me a y value of 0, f of x equals 0 here, and f of x equals 0 here. So this function has 2 real zeros at negative 3 and positive 1. So that's another way to talk about x-intercepts. They are the real zeros of a function. A y-intercept is the y-coordinate of a point where the graph intersects the y-axis. So in this case, the y-intercept is equal to -3, right? And the graph of a function can have at most one y-intercept. So stop the video and think for a minute why the graph of a function can have at most one y-intercept. So hopefully you thought about that for a minute, right? And if this graph had more than one point on the y-axis, right? The y-axis is a vertical line, right? So if I had another point up here, then it would fail the vertical line test, right? So the graph of a function can have many x-intercepts, but it can only have at most one y-intercept. Okay, so now let's put it all together and look at a couple of examples. And a good test for you, if you're feeling confident with the material that we've talked about so far, would be to go ahead and try this on your own and see if you get the same answers that I get. If you're still wanting to see some more examples, then no harm, right? Just go ahead and watch the video. But this might be a good spot for you to test your understanding to this point. So we're going to use the graph to determine A, the function's domain, B, the function's range, typo, C, the x-intercepts, if any, D, the y-intercept, if any, f of 4, and all values of x such that f of x equals 5. All right, so remember now that the domain, right, is associated with the x-axis. And I see that I have an open circle here, so that's going to be a parenthesis on my interval notation, right? Here I have a closed circle, so that's going to be a bracket, right? So this function's domain is from -5, parentheses, not including that endpoint, to 6, bracket, including that endpoint. And then the function's range, let's see if we can do this one without copying and turning it sideways, is going to extend from -4, including it, right, up to 5, including that endpoint as well, right? So the domain is going to extend as an interval from -4, including that endpoint, to 5, including that endpoint, right? The x-intercepts, if any, well, the graph is has points on the x-axis here at -4 and 1 and 5. So the x-intercepts are going to be -4 and 1 and 5. The y-intercept, if any, there is a point on the y-axis there at y equals -3. F of 4, if my x value is 4, then my y value is what? 3. So f of 4 is equal to 3. And all values of x such that f of x equals 5, I'm going to go ahead and put in a horizontal line at y equals 5. And I can see that there is only one value of x that returns a y value of 5, and that is 2. All right, so there's that first example, and if you tried it on your own, hopefully you were able to work out any difficulties that you might have had. And you know, once we're done with these two examples, I'm also going to show you some examples from the homework as well. So let's look at this next one. This one asks me to use the graph to determine the following. First, the function's domain and range. So if I think about the fact that there is an arrow pointing off towards -infinity and an arrow pointing off towards +infinity in the x direction, right? The domain is going to be from -infinity to +infinity. All real numbers, in other words. And the range is going to, now what is the least value of y that I have for this particular function? It's 0, right? So I'm going to put a bracket at 0, And there is no greatest value for y, right? These arrows indicate these y values are going to extend towards what? Positive infinity. So the range is going to be from 0 to positive infinity, right? And a lot of times people have trouble with the range because your eye is drawn to this point on the x-axis, right? And you want to say -1. But think about, what's the y value at that point? The y value is 0, right? If you need to, turn your head sideways and we can take this and we can copy it and turn it sideways, right? So we can see that, in fact, the least value of y is 0, right? Think of it as a number line, right? And if I trace down like I did here, right? With my domain, what's the smallest value of y? 0, and there is no greatest value of y, right? Okay. X-intercepts, if any, there's one x-intercept at -1. Y-intercepts, if any, there's one y-intercept at +1. F of 3 is equal to 4. And all values of x, such that f of x, or y, right, is equal to 3. I'm going to put a horizontal line through y equals 3. And I can see that, in fact, -4 and 2 both give me y values equal to 3. So -4 and 2. So this is an example of the first problem